So we missed it. They yeah, they launched, I guess, this morning. Yeah, I guess so. It came up on YouTube and said live event. I don't know. Oh no, you're supposed to know. I don't know. Flight computer controls. So it's 53 seconds. Oh, sorry about that. I thought the thing would have a volume with it, but there's no volume. Must not have it, but 37 seconds to take off. Well, we'll watch this, then we'll do dynamics. I know it doesn't blow up because a minute ago they showed it flying along with cameras on it. Oh, so it might blow up the atmosphere. Wow, it doesn't look near as good on the screen as it does. Like where they send it is where they test it to. Like they just like a rocket just to test like if they get out of there. There we go. Oh, there it is. Yep. Well, that's a shame. I like to hear. Look, that'd be cool to hear the volume. Already at 100 kilometers per hour. No, that's 100. Like almost 200. Down to 230. Oh, it climbs really fast. Yeah, I see that. It only gets back to acceleration. So, okay, so then they had, let's see. But the live event, is that what it, okay. But the true live event, oh, there's a guy talking, but see, there's that must, so it's 26,000. Look at the ice falling off of it. You know why he did that, don't you? Put the Tesla out there.
because he could. I mean, I'd put like a house and a bus full of mannequins. I mean, you might as well just start putting all sorts of stuff. Well, I sent a thing around where I don't know if anybody read it, but I don't know if I sent it to you guys. But the Germans bought some Teslas and took them over and dissected them. Apparently, Audi did one and Mercedes did one, and they said it was a very, very well built car. So that's what's happening. Is a lot of these places are taking the car, dissecting it, figuring out how it works, and trying to compete with it. That's yeah. Subaru started by doing that with Volkswagen. I did. Okay, so where'd the book go? So we're at the location. Let me see if I can. Okay, there it was. Okay, it's hard to move around. Aha, here we go. Well, back another page or two. So we're at this location now with something called instant centers. And it has a fallback from, the 20s, 30s, and 40s and 50s all the way up to today. But it was particularly useful back then because people drew stuff often. Everything they did, they drew. So if you look at it, the equation for the velocity of B relative to A looks kind of like that. And sorry, it's kind of choppy looking there. It looks kind of like this. And it turns out if you pay close attention to it, and I can get rid of that maybe. At first glance, it's a little bit confusing until you realize what's happening here. And if you were, it would be nice if this were a better picture, but this is all I've got right here. And if you had a camera that was able to keep the lens open for most cameras have an exposure time. If it's bright, it's usually 1/8,000th, 1/3000th of a second. As it gets darker, the camera will automatically adjust and keep the lens open longer to get a better exposed picture. So if you imagine that's what's happening, you can kind of see this in which all this up here looks kind of blurry. But if you were able to focus in right here, what you would see is a very clear picture at this point. And what happens is it appears at this particular instant as though the camera is showing that this is the only spot that has a zero velocity here. And it doesn't make sense until you realize the camera is attached to the ground, sitting on a tripod. That spot is attached to the ground because it's basically touching the ground there. So those are the only two spots that this is the only spot on the wheel right now that has a zero velocity. And knowing that, he comes down and starts talking about what is essentially a rigid body having an instant center somewhere, where he's basically saying this might be the path of the instant center, but you have an object moving and it'll always have an instant center. It may be at infinity though. So if you look at, for example, this object, little blob spinning around, if you took a picture of it and it was just spinning in space, where this was the velocity at A and this were the velocity at B, you just draw a straight line to the tips and you'll notice that the velocities of all of these points behave like this. So in essence, I mean, even if you went out further and want to know the velocity of that point, it would be out like that. So in essence, it's sort of a convenient way to use the diagram and a drawing of the physical body in order to determine the velocities. So what are the implications of this? Let's see, there's a ladder. And if the ladder is sliding down the wall, then if this isn't coming off the wall, then essentially this velocity has to go down and this one has to go off to the side unless it came off the ground. If that's the case, all you do if you find two velocities on a rigid body, make a perpendicular line to them and just draw them out into space, and wherever they cross is essentially the instant center. And at that instant, it appears like this ladder is rotating about that. Now, you know, and I know that, you know, half a second later, the ladder went from here down to there. So then your instant center moved to this spot. And so you can basically trace this out and find the path of the instant center. But usually in these problems, you're interested in the velocity at that instant. This is the concept of analysis as opposed to design. So how can you use this here? There's a simple, let's just work a problem, and because it's easier to do it on the OneNote than it is here. So here, I'll just grab a problem. Hang on. This one, these problems are a little bit closer tied to geometry than anything else. So here, let's pick, I mean, I hate to pick the ladder, but we might as well just pick something. Oh, I didn't bring up the snippet. Did I just put down that? I think I just did. So here we've got he says, find the angular velocity of the rod and the velocity at point C. So he's got some point C, looks like halfway in between these two. So all you do is you recognize the velocity here goes straight down. Those are wheels. So we're assuming that the wheels don't come off the ground. You draw a perpendicular line to them. You don't even have to know the direction to find the instant center. You just draw perpendicular to them. And here's your instant center. Now, at this point, it appears like it's rotating like that. So the velocity is equal to omega r. Velocity was 6 right here. And the question is what is r? Well, I've sort of messed up the diagram, but what you see is a 4 here, and you see a 5. So essentially you see a triangle, looks kind of like this, 5, 4, so that's got to be 3. So it turns out the radius of 3, or the omega, is equal to 2. Once you have the omega is equal to 2, so this is this omega. In the other sequence, it would be omega AB, because that's the link there. That's the rigid link. There's only one rigid link. So if that's the case, then you use this distance to determine that one's magnitude. So the velocity here would be equal to omega AB times this distance, or omega AB, which was 2, times that distance, which was 4. So it turns out that the velocity of point B, which I guess I should label that, B would be just 8. So those are, you know, if you look at them, they're fairly simple problems like that. And moving through the velocities is actually pretty easy. This is a case in which, get this thing out of the way. It doesn't want to move up there. Where the two perpendiculars are coalesce. And what I mean here, I'll show you what I mean. Add a page, drop the picture. So if I were to draw this in maybe a scale, okay, so maybe that's 3. If that's 3, then this length down here, this part of the gear, will be moving about half that length. So I guess that's about half that length. 1.5 down there and 3 up there. Now, if you draw perpendicular, you'll realize the perpendicular line that came out of one went to the other. And so they are not just trying to find the intersection of them, they are exactly the same line. If they're exactly the same line, you know, I think you can draw. And the best thing to do is to draw, uh-oh, that didn't work. It jumps around. Okay. Well, forget that. I have to go back to drawing a line. Oh, what did happen here? Okay. So if I drew a straight line, it would look like this. Ah, try it again. Okay, so there's a straight line. So that means all of these points basically are doing like this. Now the question is where is everything? Okay. It says, okay, now I'm reading the problem. I should have read the problem. The cable is unwound with the speed of 3, and the gear rack has a speed of 1.5. Determine the angular velocity of the gear and the velocity of its center. So, okay, let me see if I got this right. If this is the inner, wait a minute. I think I've covered over part of it. Okay. So it appears to me like the radius of the inner wheel is 0.2 and the radius of the outer wheel is 0.3. And if that's the case, then here, it means this is 0.2 and this is 0.3. So that means the distance from here to here is 0.2 times 2 plus the difference between those, which I think the difference is 0.1. So that'd be 0.5. Is that right? So it's a half a meter there. Now, if this triangular, it's a similar triangle thing, then I would say, here, tell you what. Well, I'll erase that and just write over this part. So I would assume that this distance would be twice as much as that distance. Only because this one is half as much as that one. So that gives me, let's say, 2 distance and a distance. So it'd be 3 distances is equal to 0.5, and I guess the distance would be, oh gosh, I don't know what that would be. Have our new MATLAB here. .5/3 is just what? 1/6. It's nothing more than 1/6. So if you've got 1/6, then what you're doing is you're locating this, which is, I guess you could say it's 1/6 from the bottom or 2/6 from the top. It really doesn't matter, but what your goal here is to find this distance. That distance is 0.3. This distance is 1/6. I guess you're looking at the rest of it, which is 0.3 minus 1/6. You work your way through the rest of it, which I guess, what did I just say? 0.3 divided by 6? 0.05? That doesn't make sense. What am I doing? 0.3 minus 1/6. What did I just do? Oh. Uh, 0.1333. So here. So that's the distance to there. Now, I didn't even finish up and do the next part. I should have stopped and done that. In that, I should have recognized that there was an omega here, which would have either given me, and let's make sure that, okay. Why is it not going down? I guess, here. Okay, so if I'm looking at this, V is equal to omega R. And let's say I look at the outside here. 1.5 is equal to omega, and it's 1/6, or omega equals to, you know what, this is occupying too much of the screen. There we go. Nine. Now, if I do it at the top, I should get the same number. Okay, I'm doing the wrong. There we go. Okay, so up here at the top, V is equal to omega R2. Velocity here is equal to 3. And then the omega, but the R is equal to, what was that? 2/6, because it's 2D up there. And so from that, I would get omega is equal to 3 times 3, or 9. So I get the omega being the same either way. Then the key is what's the velocity at O? And the key there is if I were able to zoom right in at O, oops, and find the velocity to the right, then this velocity right here, this green velocity at the center, or at O, would be equal to omega times R to it, and it would be 9 times this distance right here. And that distance, I think I figured that up a minute ago, and that was this one times 0.1333, or I have no idea what that is, but here. .2. So the wheel is moving to the right at 1.2 meters per second. Even though the top is being pulled to the right at 3, the rack being pulled to the left makes this thing go to the right at 1.2 meters per second. So this, I know there's a lot of junk on the page there, but conceptually all it is that if there is a wheel, and it has to be a wheel that does something like this. If you've got a wheel and say the top of the wheel is going, 5 and the bottom's going, say 2, then all you do is you draw a perpendicular. But it turns out the perpendiculars just go right through each other. It's a rare case. I mean, it's not a rare case. It's a specific case. And in that case, you draw a straight line across the velocities, and that can tell you what's happening at any point on the wheel. course, you could have a wheel that's sitting here. Here. So you have a wheel that sits here. The top of this thing goes at 5. Ah, come on. Okay. The top goes at 5. The bottom goes at 5. So if the top and the bottom are going at 5, you draw a straight line, it goes right through the center. It just means the wheel's going around and around. So you have a situation like that. So the only other case, or a case when you have multiple links, and these are kind of convenient. I don't know which one. Let's do this. This one maybe is the 14 is too simple for right now. Let's do the 17. And in the 17, there is, hang on. You have some known interesting features here. First thing you know is this thing is a wheel which is rotating around here. So I can draw a straight line up here and tell you it's rotating like this. So I know the velocity at B is going this way. Now with this, I know it's either going this way or it's going that way. It can't jump out of the cylinder. Okay, and then you just follow the rule. I mean, if the rule, you could say, draw perpendicular to velocity vectors. Okay, so then 2, where they instant center is where they intersect or cross. So if I drew a perpendicular, it would go off the page kind of like that. This is a perpendicular. I drew a, oh, that did not come out right. Okay, draw a perpendicular to that. It goes up here and just goes right to the very top. So now I'm looking at this. Now you're in there using your geometry. You know this is a perpendicular. You know this is 30 degrees. So that tells you that's a 60. You already know that's 0.8. So if I drew this a little bit smaller over here, kind of look like that, where this is 0.8, this is 60. So if that's the case, this is 30. If that's 30, I can tell you this is 1.6. Reason I know it's 1.6 is because, what is it? Sine of 30 is equal to a half, or a cosine of 60 is equal to a half. So I have those two things. Now, this being the case, I know the thing is rotating like this to get that velocity going to the left. So what you're doing in your mind here is you're saying, okay, I have a rigid link right here. That's really a rigid link. Because of that, I can tell you the velocity is going to the left. Then in your mind, you just erase this from your consideration completely, and you're only looking at this rod. When you're looking at that rod, you're looking over on another spot over here and realizing it has to slide up and down this 30-degree angle here because it's a piston, and it can't jump out of the sleeve unless it's broke. So if this is omega, then you have R. You could say instant center to C, and this is R instant center to B. It's the distance from, let's say the instant center is up here. Let's make it a big glob. So I know it's off the page. I should have, I wonder if I could do this. Oh, okay. It is not off the page here. Okay, so here's your instant center. So your instant center sits right here where those two lines crossed, and it appears as though this linkage right here is rotating about that instant center. which now just tells me I need to find this distance, because I know this velocity, it's 6. This velocity is 6 times 0.2. What's 6 times 0.2? Is that 1.2 meters per second? And how do I know that? Because velocity is equal to omega r. It just depends on which omega and which r you're looking at. In this case, this is the r, and there's the omega. That tells me the velocity of point B. But now I need to know this in order to get the omega of this link right here. So if I'm doing that, then that's great that cosine is a half, but I'm more interested now in, say, what cosine of 30 is equal to that d over 1.6. And so 1.6 times 856. So if that's the distance, then I'm just looking at one simple thing. I'm basically looking at this link and this velocity to give me the omega. So V is equal to omega r. The velocity was equal to 1.2 from right here, omega, and then the r here is this d, or 1.3856, or the omega of that whole link is slightly smaller than and the 866. Oh, that's interesting. 0.866, which is the same thing as the cosine of 30. And now that I have that, what I need to do now is find this. And now I know since this thing is rotating in this way, this velocity has to go to the left. And so take a look at that thing. And can't send it down the page anymore. Oh, there we go. So I have V is equal to omega r this time, which now I'm looking at the velocity of C. Omega, the instant center to C. Now I just insert the 0.866 times that distance, or this distance, which is 1.6, and I get the velocity of C equaling to, push the wrong button. Okay, so I can just say, it's going to be interesting what I get there, but here times 1.6. You can already see there's a 1.6 in the denominator, 1.3856. It's interesting that there are repeated numbers here, each one having a different meaning. So since it sits right there, there's the book, there it is. Then essentially all you're doing is coming in, finding the instant center, finding the rotation about it, finding this link gives you that, V is equal to omega r, and this one's going this way, V is equal to omega r, where this is the r. Over here, that's the r. The omega is the same. Okay, book, where's the book? Oh, yeah, that's the book. What am I doing? Okay, I told you, hang on. Okay, watch it.